Okay, Year 11s, good afternoon and welcome to the next series of my videos. Today the topic of conversation is oxides, and there are four types of oxides. They can be either acidic, they can be basic, they can be neutral, or they can be amphoteric. The first one that I'm going to speak to you guys about today are our basic oxides. Now hopefully, as you will remember from our previous discussions, most metal oxides are basic. Now there are a couple of exceptions to the rule, which I'll be talking about later on, but for the most part, metal oxides are basic. And that is because they react with water to form hydroxide ions. And that's you'll remember one of the definitions of a base is the formation of hydroxide ions. At this point, guys, it's also worth noting that in a metal oxide, we're looking at an ionic bond. Okay, the metal donates electrons, I should say, to the oxygen. Okay, so we're looking at ionic bonding when we're considering our metal oxides. Now, guys, if we consider, let's say, your book uses potassium oxide, so I might do sodium oxide maybe. So if we consider sodium oxide, which is very soluble in water, so we start with it in solid form and we add it to water, then we form sodium ions in solution. So there'd be an AQ down there to represent aqueous. And we form two hydroxide ions. So you guys can identify, therefore, that sodium oxide is a base. Now, that would be the case for most metal oxides. So we could replace the sodium with magnesium, or with potassium, or with calcium, and the outcome would be the same. We'd still get the relative positive ion in solution, and we would get these hydroxide ions in solution. Now, guys, because our metallic oxides are basic, they can also react with acids in neutralization reactions. Now, I'm only going to draw the ionic equation to represent this, because you guys should really be familiar with ionic equations. So let's take potassium oxide, for example. On reaction with an acid, and we've got two H plus ions there, so let's... it could be sulfuric acid, could have been hydrochloric acid, nitric acid, whatever it is, doesn't matter. Guys, this is a strong base reacting with a strong acid, so this arrow goes only one way to show that the reaction happens to completion. And we form two potassium ions in solution, and we form water, or H2O, which we know are the two products of neutralization. And this would be a solid. We can have AQ there. That would be AQ for the potassium, and obviously the water would be a liquid. So, guys, it sort of represents the sort of two key points for metallic oxides. Okay, firstly, they dissolve in water and they form hydroxide ions, and secondly, they react with acids in neutralization equations to form salts and water. So, guys, that is our basic oxides. Now, acidic oxides, I think it's fair to say, are just a little bit more complex. So, often, guys, our acidic oxides are our non-metal oxides. Now, there are a couple of exceptions to the rule, and that is chromium and rubidium are both acidic oxides, and they're both actually metals. But for the most part, non-metal oxides are acidic, so remember that. And obviously, guys, if it's a non-metal oxide, then we're looking at a covalent bond, or the sharing of electrons, as opposed to the ionic bond and the transfer of electrons with our metal oxides. So that's worth remembering. Now, there's a really easy reaction to demonstrate this is sulfur trioxide. Now we know that sulfur is a nonmetal, so this is a really easy one to look at. Water gives us a very familiar acid, which is H2SO4. So it's very easy, guys, to see that sulfur trioxide plus water gives us the very familiar acid of sulfuric acid, which we know to be a very strong acid. And if this is concentrated enough, guys, it will actually be in liquid form, not aqueous form, so you can put an L there to show liquid. Another common non-metal oxide that we could use to demonstrate its acidity is carbon dioxide gas plus water forms H2CO3, which hopefully you guys would remember as carbonic acid, the acid present in soft drinks, and this is a weak acid. So, guys, they're two fairly easy examples. The list goes on. Okay, we've got a whole range of different acids, so we could substitute this S or C with Cl in the formation of chloric acid, or P in the formation of phosphoric acid. Okay, so there are a couple of common sort of examples of that. Now, guys, if we consider the two examples that I used just now, which was carbonic acid from CO2 and sulfuric acid from sulfur trioxide, or SO3. All of these acids from non-metal oxides share something in common, and that is that they are hydroxy acids. And the word hydroxy means to have an OH group. So all of these acids, guys, from the non-metal oxides actually contain at least one OH group. This OH group is not to be confused with OH minus or hydroxide ions that a lot of bases have. Okay, they are not the same thing. So don't be confused about how these acids can have these hydroxy groups and still be acids, okay, because these hydroxide ions and this are not the same thing. Now, guys, just to demonstrate the hydroxy group setup, I'm going to draw these two acids, okay, carbonic acid and sulfuric acid, just so you guys can sort of see a bit of a pattern happening. So carbonic acid looks like this. It's got a double bond with one oxygen, and then it's got two hydroxy groups like that. And sulfuric acid has got two double bonded oxygens, and remember, sulfur is one of these freak elements that can have extended octets, so that's why there's quite a few lines that representing bonds come off sulfur, because it doesn't have to just bond with 8 in its valence shell. So guys, you can see here carbonic acid has got 2 hydroxy groups, and sulfuric acid also has got 2 hydroxy groups. So that's just something that these acids have in common, and you would need to be able to demonstrate that, guys, so learn sort of how to draw those structures. Now, because these non-metal oxides are acidic, they have the ability to react with bases or with hydroxide ions to form water and a polyatomic ion. So, in keeping with the one I just drew for you guys before about the carbonic acid, we'll stick with carbon dioxide for the time being. So, carbon dioxide plus 2 hydroxide ions yields water and a polyatomic ion. And hopefully you guys can see that really the only polyatomic ion that you can form from this setup is carbonate CO3 minus 2. And guys, all of these will be, these ions will be AQ and the water will be a liquid. Now guys, remember on the previous slide I just said that carbon dioxide reacts with water to form carbonic acid, which is H2CO3. An easy way to then determine what polyatomic ion these non-metals oxides form on reaction with hydroxide is to look at the polyatomic ion of the actual acid that they would form. So guys, to simplify that, carbon dioxide reacts with water to form carbonic acid. It would also then react with hydroxide to form carbonate ions, and you guys can hopefully see that the carbonic acid and the polyatomic ions formed share the same thing in common. I can show you another example of that, which would be sulfur trioxide and hydroxide will give you water and what ions? Sulfate ions, SO4 minus 2. And that is because sulfur trioxide reacts with water to form H2SO4, and the polyatomic ion of sulfuric acid and the one formed in the reaction with the hydroxide is SO4. So hopefully you guys can see a little bit of pattern evolving there. It might be worth getting you to ponder this question then. What do I form if I react sulfur dioxide with hydroxide ions? Well, I get water. And if you're not quite sure what polyatomic ion you get, consider what acid you get when you react sulfur dioxide and water. Well, the reaction of sulfur dioxide and water yields sulfurous acid, which is H2SO3. And hopefully that would give you some hint to the polyatomic ion formed here. It's SO3 minus 2. And you can see that this sulfurous acid and this polyatomic ion here look very similar. So guys, that is our non-metal oxides and how they, generally speaking, demonstrate acidic properties. Now guys, the next one on the list are our neutral oxides, and obviously the word neutral means that they don't really react with acids or bases, so we can just jot down that there's no reaction. No reaction with acids or bases. And an easy common example to remember for a neutral oxide would be carbon monoxide. So that demonstrates neutral status. Guys, the last one that we need to consider are our amphoteric oxides. So you will remember, guys, that the word amphoteric means can react with both an acid or a base. So amphoteric reacts with acid or base. And it's just a case of sort of practicing a couple of these because they're not necessarily obvious or easy. Now, two very common amphoteric oxides are aluminium and zinc. chromium, in addition to forming acidic oxides, can also form amphoteric oxides. So can a handful of different metals, but aluminium and zinc, concentrate on those two. So guys, if we had, for example, aluminium oxide, AlO3, as a solid, and you reacted that with an acid, could be hydrochloric acid, for example, then you form a salt and water. So the salt, this is the ionic equation, remember? So we've sort of got a setup where this aluminium oxide is reacting with an acid. So obviously the hydrogen ions, the H plus here is the acid, that's pretty obvious. So it's this is a sort of traditional acid-base reaction, if you like, yielding a salt and water. It's more complex, guys, when you react the aluminium oxide with a base. So we still have the same oxide to start with, but we've got hydroxide ions. So this is the base down here. Oops. And you form, with the addition of a little bit of water, water plays an important part in this reaction, to yield what we know is a complex ion. So we get two aluminiums bonded with 4 hydroxides. And this complex ion, guys, actually carries a -1 charge. So this reaction here, you need to know it, and there's probably no other way but to really rote learn what the reactants and what the products are, because the formation of this isn't very obvious. Guys, in similar fashion, the zinc oxide would react with the hydroxide and the water to yield a complex zinc ion. So there are our amphoteric oxides. And then the last thing, guys, that I wanted to speak to you about was taking a look at period 3, because it's very useful when considering all the different types of oxides that you can have. So in blue, obviously, we've got basic oxides, green we've got acidic, and yellow we've got amphoteric. So if you're looking, group 3 will yield you quite a handful of different types of oxides. So we've got the group 1 and group 2 metals giving us our basic oxides, which is a common theme. Okay, group 1 and group 2 usually form basic oxides. We've got aluminium oxide, which I've just explained to you guys is amphoteric, and then we've got our non-metal oxides from silicon to chlorine onwards, forming our acidic oxides. So you guys need to pay sort of specific attention to period 3 and be able to write reactions and demonstrate how the compounds in period 3 can be basic, acidic, or amphoteric oxides. So guys, that concludes the end of the acid and bases topic for us now, and next installment will be all about redox reactions. Until then, happy study.